how do we analyze that? How do we analyze the behavior of a circuit that, based on a small perturbation, begins to move one place or another? Okay, we want to analyze the dynamics of the op-amp. Okay, to analyze the dynamics, what I need to do is give you a slightly more detailed view of the operational amplifier. Okay, if the operational amplifier is not moving instantaneously between the plus and minus rail, I need to give you a more detailed model that encapsulates the behavior of the op-amp. And so let me do that. So if you want to study the dynamics of an op-amp, by dynamics I mean how an op-amp moves, okay? How an op-amp moves as I perturb the input or the output and so on. Okay, so to capture the dynamics of the op-amp, we build a slightly more involved circuit. So V plus and V minus. And okay, so this is what we've seen before, two terminals and a dependent source that amplifies the difference input here by a large amount. Okay, instead what we're going to do here is something slightly different and interpose the following circuit in the middle here. So this is a model to model the dynamics of an op-amp. So we're going to interpose a small RC circuit in here. This is R, this is C. And I'm going to call the voltage across the capacitor V star. So notice what I've done is, rather than say this is A, V plus minus V minus, I'm breaking it apart into two dependent sources. The first dependent source, which is simply V plus minus V minus, and there's an RC time constant surrounding it. And then here, I simply add on my gain, A V star. Okay, notice that if it turned out that the resistance here, for example, was 0, then V plus minus V minus would appear across V star, and this would be A times V plus minus V minus, what you've seen before. Okay, it's always good to take a look at circuits and look at what happens when some component goes to an extreme value. This would give you your basic op-amp circuit. What I'd like to do next is analyze the following circuit to understand how positive and negative feedback work together. Okay, and by understanding that, then be able to explain how a positive feedback circuit works or a negative feedback circuit works. So here's what I'll do. So this part simply corresponds to my positive feedback circuit. R2, R1. So that's my positive feedback circuit. And I'll do the same thing on this side. Okay, all I'm doing is applying both a positive feedback through R2 and R1 and negative feedback through R4 and R3 and representing the dynamics of the op-amp and then standing back and see, all right, let's see what happens to you. Okay, so I'm sticking positive feedback, negative feedback, the dynamics of the op-amp here, and let's see what happens. Okay? So what I'd like to do is impose this circuit on top of this op-amp model. So to save myself some effort, let me just go ahead and modify this circuit directly. So I get an R2 here, an R1 here, and then up here, I get a R4, R3 here. Okay? So the math is going to be just a little bit grubby, but the result is actually pretty spectacular. Okay. So all I've done is replace the op-amp with its internal circuit out here, and now we're going to take a look at what happens to op-amp dynamics when there is small perturbation. Okay? So let's develop an equation of this circuit containing a capacitor using techniques that we already know. Okay, just to give you some insight into what we're going to see, notice that if I make a small perturbation in the voltage across the capacitor. Let's say make a small perturbation to the capacitor voltage. Okay? Let's say by applying some initial condition kind of thing onto the capacitor. Then let's say that the output, let's say the output changes to K. Okay, some value K. So the change on the capacitor must have been K divided by A. And what we're going to see is what happens to the op-amp when the initial condition on the capacitor is such that this output gets perturbed to the value K. Okay, so let's write an equation for this little circuit and see what happens. Okay, recall our goal was to understand what happens when I perturb the output a little bit. Okay, here I perturb the output such that its value goes to K. Okay, and I can perturb the output by changing what happens at the capacitor. Okay, so let me write the equation for this circuit now and try to understand what happens to this capacitor circuit if I let go after giving it a small perturbation. So what I'm going to do is let me start by writing the good old equation for this little circuit here. And that equation is simply the voltage here, V plus minus V minus, equals the voltage across the RC. Okay? So V plus minus V minus, okay, will be equal to the voltage drop across the resistor plus that across the capacitor. The voltage across the capacitor is V star. The voltage across the resistor is the current through the capacitor, C dV dt, C dV star dt times R. Okay, so V star plus RC dV dt is equal to V plus minus V minus. Okay, so RC dV star by dt plus V star is V plus minus V minus. Okay, you've done this millions of times before, but yet again, this voltage here is equal to the drop across these two. And the drop across these two is V star, the drop across C, plus the current through the capacitor, C dV dt, times the resistance R. Okay, or you can apply the node method as well and get the same expression. Now we also know that here that V naught is simply, or V naught divided by A is V star. Okay, so I can go ahead and replace this guy here, V star by V naught divided by A. So it's RC divided by A, dV naught by dt. Recall, I want the dynamics of V naught, so let me just get an expression in V naught. So I get a V naught divided by A plus V plus minus V minus. Okay, equals. Now, so I want the expression in V naught, equation in V naught. So I need to express V plus and V minus in terms of V naught. Okay, so what are these expressions? So expression for V minus is V naught and this voltage divider. So it's V naught times R3 divided by R3 plus R4. Okay, and just for simplicity, let me call this some constant gamma minus. Okay, so this is some fraction. Okay, R3 divided by R3 plus R4, and let me call that fraction gamma minus. Similarly, V plus is V naught R1 divided by R1 plus R2, and let me call that gamma plus. Okay, all I'm doing is replacing V plus and V minus in terms of V naught. Okay, so effectively what I have here is V plus is some fraction of V naught. That's the best intuitive way of thinking about it. Some fraction of V naught. Okay, so and V minus is some fraction of V naught as well, like so. Okay, and I just take these okay, so I now have an expression in V naught. Okay, don't get psyched by gamma plus and gamma minus. Simply read this as replace with F1 and F2 if you like. So V naught times some fraction minus V naught times some other fraction. I'm feeding back some fraction of the output to the positive and to the negative terminals. So then, just moving things around a little bit, dividing throughout by A divided by RC. So I divide by A divided by RC plus V naught divided by RC. Okay? And what I'm going to do here in a second, V naught gamma plus minus gamma minus. Okay? So, and I've multiplied by A divided by RC throughout. So finally, collecting all the V naught terms, I get V naught times 1 divided by RC plus A divided by RC. Okay, I got a plus sign here, so I'll just reverse these two guys in there. Gamma minus minus gamma plus equals 0. So all I've done here is simply grunged through some math to express this equation in terms of V naught. And just to make it even simpler, I'll just replace this thing by 1 divided by t, much as we did for first order equations. So what I end up with is d V naught by dt plus V naught divided by t equals 0. So despite all that grubbiness, I end up with something that is very, very familiar to all of us. Okay? I went through a bunch of gyrations to substitute for V plus, V minus, and V star. But at the end of the day, okay, I got the simple expression which says dV naught by dt plus V naught by capital T equals 0, where capital T is the time constant of the circuit. And the time constant of the circuit relates to the expression in there. 1 by RC plus A divided by RC times gamma minus minus gamma plus. The gamma minus and gamma plus are the respective portions of the output fed back to the negative input and the positive input. Okay? Now, as we all know, based on, very simple intuition, that we can completely predict the behavior of a first order of an RC circuit once we know what the initial condition on the capacitor is, and once you know the time constant. That's it. Okay? We know, we are masters at the fact that the capacitor is going to behave like this. It's going to be exponential. Okay? And I do know that the time constant is capital T. Okay? And what's here? It's simply the initial condition. Okay? There is no drive input. I'm not driving this with any input here. There is no input drive anywhere here. Okay? So this is simply the natural dynamics of the system. And recall, I start off with bumping the capacitor voltage such that the output starts off being K. That's it. Okay, you should be able to write down this expression and the form of the response simply based on this. So this is what I bumped up the output to be. Okay, and by perturbing the capacitor voltage. So my output response based on this equation is going to look like that. So let's try to understand what that means. It's actually quite a lot of fun. So how do we plot that response? Okay, you all learned that the way to plot the response is plot the initial value, plot the final value, and go chook, right? It's pretty simple. So I'm going to start at K. I know that. I'm going to start at K. And I'm going to go and find out what the steady state value is. Here's where the interesting stuff comes in. The final value on the capacitor depends a lot on whether T is positive or negative. In my RC circuits that I looked at, what was T? In the very simple RC circuit we looked at, what was capital T? What is the time constant? RC. So this was RC. So this was a positive quantity. Okay, so when capital T is positive, okay, my output is going to look like this. Okay, when T is positive. And T is positive when this expression is positive. And if A is so large that I can ignore the 1 by RC term. If A is very, very large and I can ignore the left-hand term here, then T is positive when gamma minus greater than gamma plus. So when gamma minus greater than gamma plus, I have a stable circuit. This is the good old RC stuff we've seen before. Now things begin to make sense. So intuitively, what am I saying here? Okay, all the gammas and other pieces of crapola aside, what am I really saying here in English? What I'm saying here is that if the portion of the output fed to the negative input is greater than that fed to the positive input, then I have net negative feedback. Okay, so I have net negative feedback. So I'm feeding the output back to both the positive and negative inputs, and if my negative input has a stronger effect, then I'm going to see the op-amp output decay down to a value that I expect, which is going to be 0. Notice that since I'm not applying any input here, I expect the stable point for this to be output going to 0. Like I don't have any input there. So let's take a look at another situation. What happens when the opposite is true? What happens when gamma minus is less than gamma plus? When I feed back more, what happens when I do this? When gamma plus is greater than gamma minus. The opposite is true. This means that I'm feeding back more to the positive input. Okay, bigger proportion goes to the positive than the negative. What happens then? Then what happens is capital T becomes negative. Right? Now, we cannot see this happen in an RC circuit because capital T is equal to RC. But here we have a more complicated circuit, and capital T can go negative. If capital T goes negative, then this whole thing in the exponent there goes positive. If that goes positive, what should the output look like? It should go up, it should take off into never, never land. There we go. Right, I start off at 0, and I make a small perturbation, and the output should go as T divided by capital T. The dynamics of this is, it goes berserk. So it's net positive feedback. Okay, this is called a stable situation. This is unstable. Okay, what happens when capital T goes to infinity? When capital T goes to infinity, spend 5 seconds thinking about what it means physically. What does it mean for the time constant of an RC circuit to go to infinity? That means that your R and C are very, very, very large. That means that circuit is going to be very, very sluggish. Okay, think elephant. Okay, big time constant. I want to move a leg, takes a while to do that. Think big time constants. Okay, so everything's going to happen really slowly. It's like a moving in molasses. Okay, so big time constant. Okay, so everything's going to happen really, really slowly. So if gamma plus greater than gamma minus greater than gamma plus, with a huge time constant, it's going to look like this. And the output is going to look like this. I make T even larger. All right. It's going to look like this. Oops. Okay, I make T so large that T tends to 0, and in which case, T tends to infinity, in which case I get this situation. The output goes, duh. Okay? So very slow, very lethargic. Big time constant. Okay, T tends to infinity, and so if this is stable, this is unstable, this is called corresponding neutral. And there is a mechanical analog to all of this. You can show that this situation is akin to, let's add a physical well of this sort and add a ball in there and let the ball go, then the ball will come down here and settle down in a stable state. Any small perturbation of the ball will get it to come down and settle down here. Okay? The unstable situation is this situation where I have a ball sitting up here where any small perturbation will get it to zip down to a positive rail or to the negative rail. Okay? So this is an unstable equilibrium situation. And exactly the reason we got this analysis in the static situation is that this can happen. Okay, if I do this circuit here and don't perturb it, then I could get the output sitting at 0. But the slightest perturbation, okay, boom, it's going to fall down or go up. What about the neutral equilibrium state? So that can be modeled as, like a tabletop, and the ball is here. It doesn't matter where you go, there you are. So how many people saw the Buckaroo Banzai thing? Possibly well before your time. Okay. Okay. So I have this. Table here, and no matter what I do to it, it just goes and settles down wherever it is, and that's neutral equilibrium. So what this gives you is a fun view of the dynamics of the operational amplifier as I make small perturbations to it. And the even more interesting thing here is that you have the tools based on your first order RC analysis to analyze the dynamics of a simple op-amp circuit. Okay, so much so for theory. Okay, now let's get to some action here. So, all right, fine. That's very pretty and good and so on. But what can you do for me? Okay, what good does this property do for me? Okay, what can I build? So what we'll do is we'll look at the op-amp circuit and focus on the situation where I have net positive feedback. In particular, just look at this circuit with R1 and R2 and send this both to infinity. Okay, so I have no negative feedback, and I ground this. I ground this terminal here and take a look at what happens to a circuit with positive feedback and see if I can build some interesting circuits. So what you're going to do, build on a circuit called the basic comparator. And what is that? So if I have an op-amp that looks like this, and remember VS rail and minus VS supply there. This is V plus, this is V minus. I can build a very basic comparator by doing the following. Okay, all the circuits I'm going to show you, I'm going to build on this basic little circuit. So what I'm going to do is consider applying an input to the V minus terminal, applying some sort of an input, and taking a look at how the output behaves. So I apply some input V in, and if I just do that, then if this is V plus minus V minus here, then I'm going to get something that goes like this. That is, when this is positive, okay, when this is positive here, then this guy is going to go to the VS rail, and this guy is going to go to the minus VS rail. Okay? In terms of the, if I plot the same thing in terms of V in, and this is V out. If I plot the thing in terms of V in, then notice that as V in increases, this guy should go to a negative rail. So in terms of V in, it looks like this. What this says is that as the input becomes more and more positive, applied to V minus, then the output goes to minus VS. And if the input becomes more and more negative, then the output goes to VS. But this is what is called a very basic comparator circuit. It compares the two inputs and goes up if the input's in one direction and goes to the other rail if the input's in the opposite direction. So supposing I feed, I can plot this as a function of time. So let's say I plot V in. So let's say I feed some V in here. Let me just call this. I feed some V in to this circuit here. Then what do you expect the output to look like, the output waveform? For all positive V ins, the output is negative. So my output, V naught, is going to be negative as long as V in is positive. And when V in becomes negative, this one shoots up and behaves like this. So this is minus Vs. That's plus Vs. Okay? So this is my input V in. Then this guy is going to be my output. Okay, so as V in is positive, output slams to the negative rail. When V in becomes negative, the output slams to the positive rail. So that's quite nice. But, and so such a circuit is pretty useful to me. Let's say, for example, I want to build a little digital circuit that is fed ones and zeros. So I can use a comparator to turn my V in voltage into a sequence of ones and zeros. Okay, so when V in is positive, I produce a 0. When V in is negative, I produce a 1. Okay, so I can get this 1, 0, 1, 0 sequence coming out corresponding to the values of V in being greater or less than 0. Now, one problem with something like this is that this circuit can be quite messy in the following situation. Suppose I superimpose a small amount of noise on V in. Okay? So in particular, let's say that some amount of noise on V in. And so I get a bunch of noise sitting on here. So what happens is that when, at this point, where the value goes negative, I do bump up. But when, for a second, I have my input going above 0 again, this output comes down again, and out here it goes up again. So I get this nasty behavior at the point where the input is around 0. Okay, so when the input is around 0, as the input is meandering around 0 because of noise, I get a huge amount of up and down glitches on the output. Okay, that's not very nice. And we'll do a little circuit that attempts to fix that little problem. So what we're going to do is use positive feedback. And I'm going to build you a circuit that shows that we can eliminate this for small noise on the input. So let's build the following circuit. So I still feed Vi to the negative input. But this time around, I give it some positive feedback. Okay? So I give it some positive feedback. And what I'm going to do is feedback a portion of VO to the positive input. This is positive feedback. And in particular, let's assume that Vs equals 12. Vs equals 12 volts. Okay? And to the negative one, I connect minus Vs. So this guy is going to go between 12 and minus 12. And correspondingly, because these two are equal, this one is going to go between 6 and minus 6. So this is going to be at 12 or minus 12. Remember, the top rail or the bottom rail. And this one is going to be at plus 6 or minus 6. And let's understand how this circuit works when I apply a input V in. So let's start by saying that assume my input is 0 for a moment. Okay, my input is 0 for a moment, and let's say my output starts off being 12 volts. If the output is 12 volts, then the input here is going to be 6 volts. Okay, so in this case, V plus is going to be 6 volts. The output is 12, V plus is going to be 6 volts. Okay, and my circuit is sitting out there doing nothing. Okay, now, so this started off being 0. Let's say V in increases. As V in begins to increase, what happens? Well, nothing. Until V in reaches 6 volts. Since this is 6, V in has to go up to 6 volts, has to equal this voltage before I can flip the circuit. So what happens when V in is greater than 6 volts, if V in goes above 6, then I have more voltage on the negative terminal than the positive, and so the op amp flips its state, and I get to, V naught gets to minus 12 volts. So when Vi goes above 6, V naught gets to 12 volts. And what does V plus go to? So in this state, V plus goes to half of minus 12, which is minus 6 volts. Okay, so now this guy is sitting at minus 6, and this guy is sitting at minus 12. Okay, so if this one keeps rising, nothing happens. The output will stay at minus 12. Okay, so I'm pretty safe. Then let's say V begins to come down. As V begins to come down, does anything happen when V gets to 6 again? If V is equal to 6, what happens? Nothing, because this is at minus 6 now. Okay, so there is still a huge net negative voltage here, okay, from V plus to V minus, and so therefore I sit at minus 12. So, oh well, I keep going down until I reach minus 6. When I reach minus 6 here, these two become equal. Okay, and what happens when this becomes less than minus 6? So V minus becomes less than minus 6. If this one goes below this voltage, let's say this is minus 6 and this is minus 7. Okay? There is a net positive voltage between V plus and V minus. So this output swings to the positive rail like so. Okay? We'll spend a lot more time on this in the next few minutes to really hammer the point home. So what's interesting about this is that even though the moment Vi became more than 6, I swung to the positive rail, and then I had to go all the way back down to minus 6 before I could change state. Okay, so I had to go way down before it would flip again. So how can we make use of that? Well, let me draw you a little Vi versus V naught diagram, and then talk about how that can be useful to us. So this is Vi. This is V naught. This is 0. Let's say this is 12. The minus 12, minus 6, plus 6. Okay, let's plot that on the screen and see what it looks like. So as I told you, the output was at 12 volts to begin with, and my input was at 0. So my input kept increasing. When the input hit plus 6, what happened to my output? My output swung down to minus 12. As the input kept increasing, nothing happened. So this was step 1. This was step 2, step 3. If the input kept increasing, output stayed at minus 12 volts. Okay? Then what I said is, well, let's bring the input down. So my input began to go down. As step 4 became more and more negative. Nothing happened until I reached minus 6. When I reached minus 6, I swung positive. Step 5. Again, 1, 2, 3, 4, 5. I'm going up here. Came up here. And nothing happens until I reach minus 6. But at minus 6, boom, I switch to the positive rail. And as I get more and more negative, I stay there. Then again, as I start increasing again, nothing happens until I reach plus 6. Think of that as your 7th step. What is spectacular about this is that I seem to have a circuit that now has some knowledge of where it came. Okay? So if it's coming from here, it switches at plus 6. But if it's coming from here, it switches at minus 6. Okay, so there seems to be sort of a lag in the behavior of the circuit, or some memory property in the circuit. Okay, this kind of behavior is called hysteresis. Okay, the word comes from magnetic circuits where, or other elements that you're trying to magnetize, where if you take a magnet and move it over a piece of metal, it may leave some residual magnetism in it. And in the same way, that's called hysteresis. Same way here, as the voltage increases, it seems to leave some residual in the circuit so that it affects when it shifts. The good news with this is that now, if I take the same kind of noisy waveform that I had before and do this, if this is Vi, then what's going to happen is for VO, I'm going to be negative at this point. Nothing happens here because I have to get to minus 6 or plus 6 before something happens. So out here, I get to minus 6, and I switch state, and I go up to plus 12. And then this one comes up above minus 6 very slightly out there, goes above minus 6. Nothing happens because the next change will happen only when the input goes to plus 6. So eventually the input gets to plus 6, then I'm going to change state again. Okay? So this is actually a really cool property and something that is completely non-obvious. In the last 30 seconds, let me show you a quick demo. And based on this property of hysteresis, I've actually built a little circuit. Let me do that first. So notice here that I'm showing you the input on the x-axis, VI, and VO on the y-axis. So notice how the output switches at plus 6 volts, and then switches at a minus 6 volts to plus 12 or minus 12. Okay, that's a hysteresis property. And we can actually use this property to build a clock circuit, which is on page 9. Builds an oscillator that sits there and oscillates by itself. And you will see details of that in recitation tomorrow.